Okay, basically looking at balanced chemical and net ionic equations and talking about a little bit of the physical chemical change, mostly chemical change here because we're looking at signs of chemical change, and we kind of talked about those when we did the first, talking about the first set of reactions. You know, energy changes, you see a precipitate, you see bubbles. It could be, you know, bright light. It could be color change. When you have like two clear things, you put it together, you get yellow or, you know, blue or something like that. Those kind of things signify that a chemical reaction has taken place. You have bond breaking, bond forming, getting new substances. And as you'll see today when we talk about bond breaking, bond forming, or IMF breaking, IMF forming, or overcoming them, I guess is the proper way to say that, those all have energy changes, and that's why temperature can be affected and changed. So we'll get into some more detail with the energy change stuff with the thermo. But here we're paying particular attention on how to write net ionic equations from different reactions. And some, like I said, are Chem 1 stuff from last year that should be pretty easy and whatever, but then the added little extras for AP, and I'll highlight the takeaways, like I said, once again. What are the important ones? What are you going to have to be able to do here? And hopefully you'll absorb it a little bit better since we've already really looked at precipitation. We've already looked at redox and acid-base neutralization in some detail at this moment. So synthesis reactions, you know, it's two things coming together to make one thing. So that's the general idea here at the top. This is the general format. We see A plus B gives AB. Bunch of different types of them though, and I'm going to go through and highlight some other ones just for pattern purposes and for also writing net ionic equation purposes. So this is the generalized one that you learned last year in Chem 1. You have a metal combining with a non-metal to form a binary salt or ionic compound. And we can represent this from a redox perspective too, like we have solid magnesium, that's a zero charge, combining with nitrogen gas. It's also a zero charge because they're both elemental, and they form this binary ionic compound that happens to be a salt or a ionic compound. So magnesium goes to +2, the nitride's -3. So we do see the changes in the charge here. So this one's just your basic one that we learned last year of synthesis. Take two things, put it together, two elements combined to form one compound that has two elements in it. Now we're specifically looking at types of things that are reacting, like metallic oxides. Hopefully you can, you know, extrapolate from the name metallic oxide that it's a metal plus oxygen. And when it's added to water, it forms bases. Okay, so you get hydroxide as the anion. Here's an example. We have barium oxide. Now oxides, of course, you have to look at those solubility rules. Don't forget about them. This is part of the issue too. You got to kind of have a good grasp of your solubility rules, or you can glance at them really quickly to get the interpretation. That oxides are going to be solids or insoluble. But if you react them with the right catalyst or heat or whatever, like react it with water here, you can form barium hydroxide. And we see this AQ over here indicating that it's soluble in the solution. Now that can be a little deceiving on some counts, but for the most part, anything that's AQ you break apart except for weak acids. Okay, I'll talk about why we don't break apart the weak acids in a minute. So we end up getting barium hydroxide, and it's AQ. Now I listed on here the strong bases again. We went over this a couple, lessons ago, but the strong bases are going to be your alkali hydroxides because they're always soluble. So that's lithium and sodium, potassium mainly are the ones you're going to be seeing. Maybe rubidium, but rubidium, cesium, like now you're getting to heavy metals that we really don't use in the lab. So although technically they fall under this category, if it's an alkali metal plus hydroxide, it's always soluble and it's considered a strong base. The other three Calcium, strontium, barium, those are the alkaline earth metal ones, the ones in group 2, the heavy metal ones that are also considered strong. They are not completely soluble. We'll get to that aspect later, but for our purposes, since we consider them to be strong, we're going to dissociate them. And dissociate means break them apart into their ions here. That's what I mean by dissociate them. All right, so write them dissociated if they're considered a strong base or a strong acid. Anything that's a soluble on the solubility rules always gets broken apart into their ion form. So in this particular case, now looking at a different aspect, this is a non-metallic oxide, so non-metal with oxygen. Hopefully we can extrapolate that. Non-metal plus oxygen is going to, if it's added to water, it's going to form acids. Now, the non-metal attached to the oxygen in the metallic oxide keeps the same oxidation number. That's something that is just an added little extra tidbit, not that important. But say you're doing carbon dioxide bubbled through water, and of course under the right conditions it will react and form some carbonic acid here. Now, carbonic acid, we know it's an acid because it has H in the front, but it's not on our strong acids list over here. So carbonic acid is considered to be a weak acid. Weak acids only partially dissociate. Since they partially dissociate, you keep them together. You do not break them apart into their ions. So that's one of the important takeaways from today. If it's a weak acid, you have to keep it together. And the only way you can really tell if it's a weak acid is if you know the 7 strong. If it's not on this list, keep it together. That's basically how you have to know it. So follow any of these strong acids, break apart. If it's a weak acid, because it's not on this list, you keep it together. So that's one of the main takeaways from today. Weak acids always stay together. Even though there's an AQ here, which is our general reason of splitting it apart, weak acids have to stay together because they partially dissociate, minimally dissociate. Most of them dissociate less than 5%. So it's really a minimal amount of dissociation that occurs. All right, this one's also showing you a non-metallic oxide being added to water to form an acid. However, the main difference in this example as to the previous one, this is dichlorine heptoxide reacting with water. Our product happens to be perchloric acid. The perchloric acid was on the strong list. It's one of the strong ones, so you have to break it apart into its ions. And technically we would put AQ here. Now the gases and liquids and solids always stay together. You never ever break those apart. The AQs you usually break apart except for if it's a weak acid. Here it happens to be a strong acid, so we know that it completely dissociates. So you want to break it apart into its ions. And nothing on either side of the arrow is the same exact phase and everything, so you wouldn't want to cancel it down. So this results in the net ionic. If you wrote it like this for the net ionic, you would not get the point. You would have to break it up into the 2 sets of ions there for the strong acid in order to get the point. Metallic oxides combine with non-metallic oxides to form compounds with polyatomic ions. This is just a general pattern thing that you'll see. You know, the calcium oxide here reacting with the sulfur trioxides, giving you calcium sulfate. Now the key to this one, like I said, this is not that important, but it's just a usable pattern that you can, you know, extrapolate. That if you're looking at the nonmetal here, the sulfur is going to maintain its oxidation number. So it's going to be a +6 over here. That's why we know it's going to be sulfate rather than sulfite, because if it was sulfite, it would be a +4. So it's maintaining its oxidation number. So I know I can predict which polyatomic ion it's going to form because of the oxidation number. And note, you know, this is solid, this is gas, this is solid. So there's no water, there's no aqueous here. Okay, we wouldn't break anything apart. This would just be the overall equation. Metallic carbonates decompose into metallic oxides and carbon dioxide gas. This is a normal pattern. So we get the carbonates, something with carbonate over here is going to give you carbon dioxide. This is decomp because you're starting with the one reactant and it's breaking down into two or more products. So that's the generalized, trend of decomp. Opposite of synthesis. Synthesis, you take things, put it together, and form one product. Here we're taking a reactant and breaking it down into its pieces. So the generalized idea there of the decomposition reaction. Now they could ask you a question about what shows that a reaction took place or a chemical change has taken place. Well, you might say it bubbles out, you see gas, okay, that kind of thing being observed. You can do different tests for it too, like we do the match test where you can light the match and stick it in the test tube and it will go out and extinguish. Well, that's because carbon dioxide, puts the light out, whereas like if it was oxygen gas, it would get brighter because it'd be feeding the fire. And like hydrogen gas makes a really huge loud popping sound. So there's different ways to test for the different gases that are being produced, but notice that a production of a gas, that would be an indication of chemical change. Metallic chlorates decompose into metallic chlorides and oxygen. Sodium chloride is heated. So we have the chlorate here, oxygen, and then we get metallic chloride as our product. Basic thing here, just another pattern showing you're going to get oxygen gas. And like I said, you could test for that. And notice that if you put the match near it, the flame would get brighter. Or like the stick, you would light a wooden stick, like a coffee stirrer kind of stick. And if it were to get brighter, you would know it would be oxygen. If it would extinguish, you would know it was carbon dioxide. And then, of course, made the really large popping sound, it was hydrogen gas. That one always freaks me out, by the way. All right, some more decomposition one, and we're going to be doing a lab with the redox titration is going to have the hydrogen peroxide in it. So hydrogen peroxide, you can buy it at the store. It comes in a brown bottle, and it's a good disinfectant for like cuts and stuff. It's better than using alcohols because it doesn't sting as much. But the basic breakdown of hydrogen peroxide is to form water and oxygen. This is also a famous reaction. It's called like the elephant toothpaste reaction. They showed it in Grey's Anatomy a couple seasons ago and also The Walking Dead. But basically what you do is you put hydrogen peroxide in a big container, you dump some soap in there, and then you add a catalyst. Now, hydrogen peroxide always decomposes. It's just at a very slow rate. But you add the catalyst, then it immediately reacts. And then if you have the soapy bubbles in there, it looks like elephant toothpaste, and it just like comes out. You can definitely Google that. But we are going to be looking at a redox that involves the peroxide here and analyzing it. Knowing that, water and oxygen are your two products here is probably good. But that one's always a good, famous reaction. And like I said, if they're going to use a peroxide in a reaction, it's typically hydrogen peroxide, although there are other ones. And remember, on peroxides, it's O2 - 2, so the charge is just slightly different here. Ammonium hydroxide. Ammonium versus ammonia, these kind of go in pairs, and I want you to notice that as a pattern. They're like the Bronsted-Lowry conjugate acid-base pairs. You see them paired together a lot of times in reactions because they are derivatives of each other. They kind of go in that pair shape. One thing you'll notice with the ammonium hydroxide, you get ammonia gas and water as it breaks down, and this actually has like a fishy smell to it. It's also in Windex, kind of, in a small amount, but if you get too much ammonia, it smells really fishy. Definite pattern here. This is decomp. Once again, you're having one reactant break down into two products over here. But one of the products with an ammonium is going to end up being ammonia gas. It's a pattern that we see lots of. Now, sulfurous acid This is the one with SO3 or sulfite in it. It breaks down, and it's a weak acid. You notice it's not on your strong list. It's not a strong acid, so it stays together. We're going to keep it together. It breaks down into water and sulfur dioxide gas. So that's a normal pattern. We're going to revisit this when we get to double replacement, because if you get sulfurous acid as a byproduct, it automatically decomposes. So it's sort of like a secondary reaction to the primary reaction. Carbonic acid acts the same way, and carbonic acid, we've already discussed, is a weak acid, stays together, it's not on our strong list, and it's going to break down into water, which is a typical product, but the other gas, remember we talked about carbonates, usually is carbon dioxide. So carbonates go with carbon dioxide gas as a product. So that's a typical pattern. This is one where it combines the ammonium with the carbonate. Now, if you paid attention on the previous slide, you would know the ammonium is going to translate over here to the ammonia gas. The carbonate, of course, is going to produce the carbon dioxide gas. So that one kind of combines the two together, and of course you see water is also a product here. The ammonium changes to ammonia, and the carbonate is going to ultimately become carbon dioxide gas as the product. So hopefully you're starting to see these patterns, make it a little bit easier to extrapolate. This one is an interesting one, and we probably won't get into huge detail with it till we get to electrochemistry, because this is electrolyzed stuff. But you know, ionic compounds typically have really high melting points. So if we're looking at like potassium nitrate here, this is an ionic compound, so its melting point should be high, really, really high. So in order to electrolyze it, where you want to have the ions free to move to conduct electricity, that's the whole electrolyze process. And this is a redox idea here, but it has to be melted down into its molten or liquid stage. So in order to melt an ionic compound, it has to be at super, super high temperatures. So when you do get the resulting melted compound, it is really molten. It's like lava. It's super hot. But then you can run the electrolysis process and end up producing your products. In this case, if you were trying to electrolyze this compound, I think what would be trying to be gained, of course, would be the potassium solid, unless they're really trying to collect nitrogen gas, which I seriously doubt, because there's plenty of nitrogen gas in our atmosphere. But they're trying to isolate the potassium solid. That would be kind of the purpose of doing this. And they do this with lots of these compounds in order to isolate certain metals and have them come out and be produced, you know, to be used as other reactants for other processes. So this is the only time really the electrolysis where you're actually going to see the liquefied version of the ionic compound, where it's really molten. And like I said, we'll talk about this in more detail when we get to Unit 9. But it still follows the idea of a redox, because you're starting off with +1, -3, and then you get 0 and 0. So you do see that this is a redox reaction, you know, as disguised as just a decomp, but it really also falls under the redox umbrella. All right, let's look at the activity series, okay? Single replacement reactions, we use the activity series to determine whether they're going to occur or not. Now, you probably saw a series like this last year in Chem 1, where it lists the metals. Here's the highest activity, which is lithium, all the way down to the lowest activity, which would be gold on the activity series. That is one way that we represent it, and we just say, you know, the more reactive metal can replace a less reactive metal in a compound. And hydrogen's on here too, because it can also act as a replacer, okay? However, for AP purposes, we're going to start looking at it from redox perspective. And here they give you the oxidation half reactions. They're showing you the oxidation half reactions. Now, in your book, they're going to be listed as reduction potentials, where they're showing the reduction potentials and how much electricity, you know, can be conducted with those half reactions. But it still follows the same pattern. The most reactive, the most oxidation, one that can be oxidized will be at the top. In that case, it's lithium, which matches over here. And then of course gold over here, least reactive for oxidation on the list. But it's showing you the half reactions now in terms of oxidation. So that's a little different, a little step up from regular chem. But we will get into these kind of tables in more detail with Unit 9. Okay, so that's the electro stuff. Now, single replacement, we have to follow the activity series. And I guess I should have highlighted the halogens too, but we can do that in just a second. This is very similar to the one that we worked in the last set of notes with the redox, where you didn't have to do it in aqueous acidic solution. This one is just the standard single replacement. You know, you have your calcium solid plus your iron 3 chloride aqueous solution. So that means this is soluble. This is a soluble ionic compound. So we would break it apart. That's why it's broken apart into its ions here. Here you have the solid iron and then the calcium chloride, which is also soluble salt. So you break it apart into its ions. Once you get it broken apart into its ions, then you cancel. The chlorines are going to, or the chlorides are going to cancel because they're spectators. They're on both sides. They're not participating in the reaction. This is very similar to that zinc chloride one I did in the last set of notes. Chloride is a spectator ion. You cancel those out for net ionic purposes. So your net ionic is just showing the ones that are reacting. And I guess technically we should also have our AQs here, showing that they are, you know, if they're ions, they've got to be dissolved in solution. So when you look at solubility rules, if it's soluble on the solubility rules, it breaks apart because it's assumed that it's going to dissociate or break apart when it's surrounded by waters and all of that other stuff. So definitely a redox here. Single replacement also follows the redox pattern because you have like the 0 going to +2 over here, and you have the +3 over here going to 0. So you do see charge change. It definitely falls under the redox umbrella as well. Active halogens. Now, halogens follow an activity series of their own. Fluorine is the most reactive, iodine is the least reactive, and we're only focusing on those four, of course, in the category. So in order for a single replacement to occur, the nonmetal, the halogen has to be higher up. So chlorine is higher up than iodine on the periodic table. So it has the ability to replace it in the compound. Now, we're reacting the chlorine gas with the aqueous Ki. So you remember this is going to be broken apart into its ions, like so, because it is soluble. Same thing over here. These are going to be broken apart into their ions as well, like so. And this is AQ, of course, just like up here. The iodine becomes a solid because, you know, remember fluorine and chlorine are gases, bromine's a liquid, and iodine is a solid in that category. It's a very strange situation. But in this case, it's also going to be considered redox because our potassiums are spectators. They cancel out. Their charges don't change. But if you're looking here, we have 0 for our chlorine. These are -1s, -1, and 0. So this is also representing a redox, canceling out the spectator ion to get the net ionic equation. So you would have to write it this way, of course, with your little AQs here, in order to get the point if they asked you to write out a net ionic equation. If you just wrote this out here and that's the net ionic, because you don't cancel out the potassium spectator ions, it would be considered incorrect. All right, another example of single replacement. This one is where the hydrogen is being replaced. The sodium was higher up on the activity series than hydrogen, so it's going to come over here and bump it out, kick out the hydrogen, and you get sodium hydroxide as a product, and you get the hydrogen gas as a product. Now that's another reason why, like, group 1 metals are called alkali metals and group 2 metals are called alkaline earth metals, is because they produce bases in water. So if you see that, here's our water is our other reactant here, and you see the hydroxides being produced. So that's kind of another, you know, little side tidbit about why they are named what they're named. However, the other little added extra for the net ionic here is you have to remember that sodium hydroxide is a strong base and it's aqueous, so you would break it apart here. sodium plus the water, and this would be like AQ here, and this would be like AQ here. So in order to get the full point from the net ionic, you would have to break those apart into their ions. This would not get the point for the net ionic. Another example here, active metals being replace hydrogen in the acids, produce the ionic compound and the hydrogen gas. So this particular case, the lead is more reactive. It's going to kick out the hydrogen here. Okay, but lead to chloride, remember lead is one of those exceptions on the solubility rules with like silver and mercury. So it's going to precipitate out and form a solid. You also get hydrogen gas coming off. So that's another thing to indicate looking at solid here. You don't break that apart. However, we are going to break apart our hydrochloric because it happens to be a strong acid. So you need to change this one into its ions and break it apart in order to get the point for the net ionic. So the solids and liquids and gases you leave together, aqueous you break apart unless it's a weak acid. That's the basic trend you need to follow. And how do you know if it's a weak acid? You have to know you're 7 strong. Everything else is considered weak. All right, this one showing another example of reacting with acid. In this case, though, nitric acid is being reacted with the lithium solid. And you get lithium nitrate and hydrogen gas. So there's slight little differences in this one than the previous example. And this is why. Nitric acid, of course, is strong. It's on the strong list. So you break it apart. Lithium nitrate. Nitrates are always soluble. Nitrates are always soluble on the solubility rules. So this one you would break apart too. And if you break these apart into their respective ions, what you'll notice is the nitrates will cancel because they're spectators. So then you have to merge it down into just the individual, the hydrogen ion, the lithium ion, and then the gas and the solid. So in order to get the net ionic equation point here, you would have to cancel out the nitrate spectators. You would have to know to break them apart because nitric is a strong acid and lithium nitrate is going to be a soluble salt. So those are important added tidbits. Nuances that, make it slightly different than the previous example. I think this is the last example, hopefully it is, of single replacement. This one is showing the sodium reacting with acetic acid. Everybody remembers acetic acid's vinegar, but it's a weak acid. It falls in the weak category. It's not part of the 7 strong, okay? So we end up getting sodium acetate and hydrogen here. Well, since this is a weak acid, you keep it together. You cannot separate it here. However, on the solubility rules, acetates are always soluble. So are alkali metals. They're always soluble on the solubility rules. So this one you would break apart into its ions here. Break it apart into its ions. So in order to get the correct net ionic, you have to keep this one together because it's a weak acid. You have to separate these two because they are a soluble salt. I know. Wow. It's quite a lot, but you'll hopefully start to notice those patterns. Double replacement reactions. The formation of a precipitate. So how do you determine that? You need to look at the solubility rules. Have those out. Try to have 1 and 2 on the solubility rules memorized because that's helpful. Try to also know that like silver, lead compounds, those ones are always going to be exceptions, stuff like that. Try to, get some of those memorized. It'll go faster. Formation of the gas. This is following those decomposition rules. We're revisiting like the sulfurous and the carbonic and the ammonium compounds, ammonium hydroxide. And then the acid-base neutralization is considered part of the double replacement reactions where you have 2 things switching here. We kind of went over this in detail already, but we'll touch on it briefly. So precipitation, look at the solubility rules. Like I said, like the silver compounds are usually going to be precipitates or solids. break up everything else that's AQ because they would be considered soluble on the solubility rules, and then cancel down the spectator ions. So in here, the potassium and the nitrates end up being spectators, like they ended up canceling. So you're left with your bromide and your silver, and that forms silver bromide. When any of these compounds are produced in a double replacement reaction, they automatically are going to decompose. So I say they're produced by a double replacement reaction. That's like the primary reaction. They automatically decompose is like the secondary reaction. So you have to remember to automatically decompose them if it's not given to you. Carbonic acid is going to automatically decompose into the liquid, water, and the carbon dioxide gas. And I don't know if you know this, but this is that volcano experiment where you take vinegar and sodium bicarbonate or baking soda. If you mix those two solutions together, it like forms bubbles, and you can put red food dye in there and it looks like it's like the volcano or whatever. That is because the bubbles are because of the carbon dioxide gas that's being produced, because carbonic acid is one of the primary products. Sulfurous acid, once again, is going to break down into water and sulfur dioxide. And then the ammonium hydroxide is going to break down into ammonia, gas, and water. So water is a product of these, but then we have our individual gases that go with, the carbonates, carbon dioxide, the SO3, SO2, and then, of course, ammonium changes to ammonia. Now let's take a look at examples of where this actually takes place. For instance, potassium carbonate added to acetic acid. So here are our original ones added together. Weak acid stays together, okay, so that's weak. But we end up getting carbonic as a product. And this is the one that's going to automatically break down into CO2 and H2O. So we wouldn't keep this in here. We're going to break it down into the two products, like so. Now, in addition, this gets more complicated because now we have to deal with our spectators. The carbonate here, potassium carbonate, this is soluble, so you have to break it apart. The potassium acetate's also soluble, you have to break it apart. You don't break apart the acetic acid because it's weak, and you can't do anything with the liquid or gas here. So you break apart those two, you cancel out the spectator potassiums, and you end up with your net ionic here. Okay, so this would be AQ, and this would be AQ. So that one has multiple steps to it because you have to remember to break down the carbonic into carbon dioxide and water, and then you have to do the spectator stuff and make sure that you cancel those out at the end. Formation of the gas, now we're looking at one that produces sulfurous acid. Okay, we're going to produce sulfurous acid here. So we know this one's automatically going to break down into H2O and SO2. Okay, now we leave this one together because it's a solid. This is hydrochloric though, so that's going to put us in the strong category. We need to break this one apart. That one needs to be broken up. And this one is a soluble salt, so this one's going to have to be broken up. Okay, so we're going to break those two up. When you do that, okay, what you'll notice, the chlorides end up being spectators. Everything else stays in here. We have our hydrogen ions and our magnesium ions that participate in the reaction. So the chlorides do, though, end up canceling out and would be spectators in that case. Last one, ammonium fluoride being added to potassium hydroxide. You get ammonium hydroxide and potassium fluoride. The ammonium hydroxide was produced, so that means this is going to be NH3 plus H2O here. So we break that down immediately. Now we look to breaking up here. Ammonium on the solubility rules is always soluble, break that one apart. Strong base, break that one apart. KF, fluorides are usually soluble except for with, I think, alkaline earth metals. So that one is soluble, you'd have to break it apart. Once you break them all apart, what you'll notice is the fluorides cancel, and the potassiums cancel. So those are both spectators here. You end up getting ammonium plus hydroxide gives you ammonia gas and liquid water. So these guys would be AQ. Solubility rules, looking at strong acids. These are the ways to know what you need to break apart and what you need to look for canceling for spectator ions. Acids and bases. We know that the acid reacts with the base that produces salt and water. 1 mole of the H plus ions will react with 1 mole of the hydroxide ions to produce 1 mole of water. That's the basic net ionic for neutralization. All right. H plus OH gives you 1 mole of water. We know that already. Strong acids and strong base will dissociate. They break apart. Weak acids and weak bases stay together. Now, you don't really have a good idea of what we're talking about here in terms of weak bases, because weak bases are going to be ammonia derivatives, but we'll get to those in Unit 8. The weak acids, though, if they're not on that 7 strong list, keep them together. Must pay attention to the amount of acid and base that are reacting. All right, so hydrofluoric is added to lithium hydroxide. This example, hydrofluoric, happens to be one of the weak ones. It's the only halogen that's weak. Hydrochloric, hydrobromic, and hydroiodic, those ones are all strong. But hydrofluoric is weak, so you keep this one together. Break apart the lithium hydroxide because it's strong. Keep the liquid water together and break up the lithium fluoride because it is also a soluble salt. So of course, then in this particular case, the lithiums end up canceling and you end up with just the fluoride in your net, the hydroxide in your net. Keep the weak acid together. Now for moles, and we're going to get into this example a lot more detail in Unit 8. But we've been looking at neutralization, completely getting it to pH of 7, that equivalence point, that's what we've been doing. But if you don't have equal amounts to get to that equivalence point, it's not going to completely neutralize. Especially for something like, this is phosphoric acid. We consider this to be triprotic because it has 3 hydrogens in it. So you would need triple the amount of the hydroxide in order to pull off all of those H's and create water from them. So in this particular case, when we're looking at 1 mole of the phosphoric with 1 mole of the sodium hydroxide, you're only going to be able to pull off 1 H from the phosphoric acid. So what the resulting product is going to be the dihydrogen phosphate. If we wanted to get all of them off and we wanted to remove all of the hydrogens, this would need to be 3 moles to the 1 mole. But it's not here. We're saying 1 mole to 1 mole. Once again, though, the sodiums are going to cancel because those are spectators and they're always soluble. So you would end up with your phosphoric acid, which is a weak acid. It's not on the 7 strong list. Your hydroxide ion, liquid water, and then your dihydrogen phosphate ion. That's if it's 1 to 1 mole, because 1 hydrogen plus 1 hydroxide gives you 1 water. If we wanted to neutralize the entire thing on the phosphoric, we would have to use 3 moles to every 1 mole. So that's just, keep in mind that it's a stepwise deal, and you need 1 hydroxide for every H. The combustion reactions, and there's not a whole lot to these really completely, but we know that we get carbon dioxide and water as a product if it's complete combustion. Now, usually you have some kind of hydrocarbon plus oxygen. Those are your reactants here. And then you get the CO2 plus the H2O. This is a regular combustion reaction. And we're talking like propane, octane, regular fuel type stuff. If there's enough oxygen, it will completely combust and you'll always get carbon dioxide as a product. If you do not have enough oxygen, you end up getting some carbon monoxide as a product because you don't have enough oxygen to completely bond up to create carbon dioxide. So that's an additional product where you have incomplete combustion. Now, just to also talk about combustion reactions in general, some combustion reactions also have additional, they'll have additional non-metals attached here to your organic compound, like sulfur or chlorine or nitrogen. If that occurs, you're going to get an additional product that has either like nitrogen dioxide that has that gas in there, or you'll get sulfur dioxide, or you'll get some kind of chlorine compound. If you have additional nonmetals attached to your organic compound, you will see additional gaseous products usually being produced here. The only thing, though, different between complete versus incomplete is the amount of oxygen, this part that goes in. If you have enough, you should get carbon dioxide always, formed. If you don't have enough oxygen, it runs out. Sometimes you'll get some carbon monoxide, which we know is very poisonous and bad. And you wouldn't want to breathe too much of that in.